Chapter 21 will cover the reactions of carboxylic acid derivatives, specifically a reaction called nucleophilic acyl substitution reactions. Before we begin covering acyl substitutions, let's review some of the functional groups we're going to encounter in this chapter. All of these functional groups are related in that they're all acid or carboxylic acid derivatives. Acid chlorides are compounds that contain a chlorine attached to a carbon with a carbonyl. Simple example is acetyl chloride, which is shown here on the right. Acid bromides contain a bromine that is attached to a carbon with a carbonyl or is part of a carbonyl. An example is benzoyl bromide. Acid anhydrides, or simply anhydrides, are compounds that contain an oxygen in between two carbonyls. A simple example is acetic anhydride. Esters contain an alkoxy group attached to a carbon of a carbonyl. A simple example is ethyl acetate. And amides contain an amino group attached to a carbon that is part of a carbonyl. A simple example is acetamide. Amides can be further subdivided into primary amides, secondary amides, and tertiary amides. Primary amides contain no alkyl groups, and therefore the nitrogen of the amide has two hydrogens. Secondary amides contain one alkyl group, and they have, as a result, a hydrogen on the nitrogen. And a tertiary amide contains two alkyl groups on the nitrogen, and therefore no hydrogens on the nitrogen. Esters are well known for, at least simple esters, are well known for the smells, the pleasant smells that they contain. For example, isopentyl acetate is responsible for the smell that we normally associate with bananas, and methylbutanoate gives apples their typical aroma. There are two additional acid derivatives that you should be familiar with, although they're often not used in organic synthesis. In a typical organic lab, they are important acid derivatives when it comes to biological systems. So those two acid derivative functional groups are thioesters, which contain a sulfur attached to a carbonyl, and acyl phosphates, which contain a phosphate group attached to a carbonyl. These functional groups we're going to cover, or we're going to see a few examples as we go through this chapter, but in general, they're not really used in organic synthesis. Here's an example of a molecule that contains a thioester. You can see that here on the right side, there's a carbonyl with a sulfur. This is acetyl coenzyme, which is a thioester. We're going to look at the importance of this thioester later on this chapter. With the exception of carboxylic acids and primary and secondary amides, most acid derivatives will interact with each other through dipole-dipole interactions as well as London interactions. As an example, here is an ester. It has a boiling point of 32 degrees Celsius. An acid chloride has a boiling point of 51 degrees Celsius. Compare that to a carboxylic acid, which has a much higher boiling point. We could explain this by the fact that carboxylic acids interact with each other through hydrogen bonding, while an ester and an acid chloride would interact with each other mostly through dipole-dipole interactions as well as London forces. A primary amide, such as acetamide, has a very high boiling point of 221 degrees Celsius. This is because it's able to hydrogen bond. In the case of a primary amide, it can actually form more hydrogen bonds compared to a carboxylic acid. So that sort of explains why a primary amide would have generally a higher boiling point than a carboxylic acid and even an alcohol. In this example, you might notice that the acid chloride has a slightly higher boiling point than the ester shown, even though they're similar molecular weights. The chlorine is a heavier atom than oxygen and carbon and hydrogen, which are found in this ester. And so for that reason, it leads to a slightly higher boiling point for the acid chloride. Acid chlorides are named based on the carboxylic acid that would be used to make that acid derivative. As an example, acid halides, which includes acid chlorides and acid bromides, in order to name them, we had to convert the carboxylic acid name. In particular, we got to change the ic acid ending to a YL followed by the halide, chloride or bromide. As an example, here we have acetyl chloride. So this compound is named from the carboxylic acid that it came from. So that carboxylic acid would be acetic acid, which has this structure. It has a carboxylic acid and it has a methyl group here. So this compound, this carboxylic acid, if we replace the OH group with the chlorine, we have acetyl chloride. So we derive the name from the carboxylic acid, which is acetic acid. We change the ic acid ending to YL, right? So acetyl, and then add the halogen, which is chloride. So acetyl chloride would be the name for that compound. The next acid derivative here is benzoyl bromide. So we have changed benzoic acid into benzoyl bromide. This next example has 1, 2, 3, 4, and 5 carbons. It is an acid bromide, so this is named as pentanoyl bromide. If we had an OH here instead, it would be named as pentanoic acid. So we drop the ic acid ending, replace it with YL bromide. We also have a substituent on carbon 3, a hydroxy substituent. So that is added in front of the name, 3-hydroxypentanoyl bromide. And then lastly, the stereochemistry is S around carbon 3. So you can determine that by the fact that this oxygen has the highest priority around carbon 3. Then between carbon 4 and 2, we have 2 identical CH2 groups. The second carbon is bonded to another carbon, which has bonds to oxygen, bonds to bromine, while this one, carbon 4, is bonded to carbon 5, which has only hydrogen. So this is a higher priority group than carbon 4, which would be priority number 3. There's also a hydrogen facing back here, which has the lowest priority. So we can ignore that for now. So we go from 1 to 2 to 3. Notice we're going counterclockwise, so that is S stereochemistry. In the last example here on this slide, we have a compound that has an alkene. It has an acid chloride group. The carbon of the carbonyl is the highest priority carbon. So we start counting there. 1, 2. Then we go in this direction to include the double bond. So 3, 4, and 5. So this is a pentanoyl chloride, right? We have also a double bond, so it's actually pent 3-ene oil chloride. And then we have a substituent on carbon 2, which is an ethyl group, so 2-ethyl. And then lastly, we look for stereochemistry. The only stereochemistry here is this double bond. Notice carbon 4 has a methyl group that way. It also has a hydrogen this way. Between carbon 5 and this hydrogen, the carbon labeled as 5 has a higher priority than the hydrogen. And on this side, we have a hydrogen, and we also have the carbon that we labeled as 2, which has a higher priority than the hydrogen. So the carbon 2 and carbon 5, which is the two highest priority groups around this double bond, they're on opposite sides, so this is the E isomer of this alkene. Symmetrical anhydrides, for as far as naming, we're going to change the acid ending of the carboxylic acid that is used to make that anhydride with the suffix anhydride. So as an example, this symmetrical anhydride, if we split it in half and turn each side to a carboxylic acid, we actually have 2 molecules of propanoic acid hidden with this anhydride. So again, imagine splitting this anhydride down the middle and turning this carbonyl into a carboxylic acid, which would look something like this. And the same thing happens on the right side since it is a symmetrical anhydride. So notice, if we ignore the oxygen in the middle, notice there are 2 molecules of propanoic acid hidden within this anhydride. And so we would name this compound as propanoic anhydride rather than propanoic acid. In the next example, again, if we split the anhydride down the middle and think of the left side and the right side as 2 different carboxylic acids, we would name those carboxylic acids as acetic acid. That's the common name for it. Or if you want to use the IUPAC name, it would be ethanoic acid. If we change the acid ending with anhydride, we have the name for this anhydride. So it's acetic anhydride. The next example, again, if we split this in half and turn each half into a carboxylic acid, we would have benzoic acid. So this anhydride is named as benzoic anhydride. For unsymmetrical anhydrides, we have essentially 2 carboxylic acids joined together to make the anhydride. So in order to name unsymmetrical anhydrides, we give the names of the 2 carboxylic acid compounds hidden within that anhydride, and we ignore the acid part. We replace that with anhydride. The 2 carboxylic acid names will be named in alphabetical order. So as an example, this compound here, if we split it in half, and again, if we imagine adding an OH group where this oxygen is attached, and we ignore this oxygen for now, and if we put another OH group here, the 2 carboxylic acids that would be used to make this anhydride, which we'll talk about later when we cover reactions, would be acetic acid from the left side and benzoic acid from the right side. So putting those in alphabetical order, this anhydride would be named as acetic benzoic anhydride. In naming esters, we're gonna give the alkyl group that is attached to the oxygen of the ester in front of the name, followed by the suffix ate, which is going to replace the suffix ic acid from the carboxylic acid. So as an example, we have here a compound that if we think about which carboxylic acid this came from, we would have to ignore this part and put an OH here. If we were going to name this carboxylic acid, we would name this as it has 3 carbons. So it has 1, 2, and 3. This would be named as propanoic acid when it's a carboxylic acid. It has a methyl group on carbon 2, so it would be named as 2-methyl propanoic acid if it was a carboxylic acid. When it is an ester, we change the ic acid ending with ate. We also have an ethyl group on the oxygen of the ester. That ethyl group goes in front of the entire name, so this entire compound is named as ethyl 2-methylpropanoate. The next example has an ester that, if you think about which carboxylic acid it came from, it would be benzoic acid. So again, ignore the alkoxy group on the ester for a moment. We would have this carboxylic acid. So the compound as an ester is named, instead of benzoic acid, is named as benzoate. So drop the ic acid ending of the carboxylic acid and replace it with ate, and you have the parent name for the ester. We also have an isopropyl group on the oxygen of the ester, so that goes in front. If there were any substituents, those substituents would go in between this isopropyl and benzoate. The next example has a terp-butyl group on the ester, so that goes in front, terp-butyl, followed by, we have 1, 2, 3, 4 carbons, so that is named as butanoate. This last simple example has an ethyl group on the oxygen of the ester, so it's named as ethyl, and then the rest of the molecule is named as acetate, since it comes from acetic acid. Naming amides is slightly more complicated than the other acid derivatives. The way we go about it is, at least for primary amides, we simply replace the ic acid or oic acid suffix for a carboxylic acid with the suffix amide for amides. So as an example, if we have 6 carbons in the amide in the parent chain, and we have a primary amine, we would name this as a hexanamide to indicate there are 6 carbons and it is an amide. In the next example, we have 5 carbons in the parent name, so this is named as a pentanamide. We also have an amino group on carbon 3, so 3-amino. And then notice carbon 3 has stereochemistry, which is R, and we can confirm that by the fact that we have an amino group, the nitrogen, which is the highest priority group directly attached to carbon 3. We have this carbon 2 and carbon 4, which are both CH2 groups. They're identical groups, so we want to move on to the next groups attached, which is carbon 1 and 5. Now, carbon 5, notice, has a carbonyl, while carbon 5 has only hydrogens. So that means that carbon 2 is the second priority group, and then carbon 4 is the third highest priority group around carbon 3. So if we go from 1 to 2 to 3, we're going to go in a clockwise fashion. So that means that the stereochemistry of carbon 3 is R. For secondary and tertiary amides, it gets a little bit more complicated. When it comes to secondary and tertiary amides, we have alkyl groups attached to the nitrogen of the amide. And we indicate those groups by the locant N, meaning the N, capital N, tells you that you have an alkyl group on the nitrogen of the amide. Now, if you have 2 of the same alkyl groups, we would use the prefix N, N to indicate that we have that particular repeating alkyl group on the nitrogen. We also have to replace the suffix of the carboxylic acid where this amide came from being ic acid or oic acid to amide. Here's a few examples actually. The first one has carbonyl of the amide plus another 4 carbons in the parent chain, so there are 5 carbons. and this is an amide, so it's named as pentanamide. We also have an ethyl group on the nitrogen, so that's added in front, and so we name this as N-ethyl pentanamide. With the next example, we have two methyl groups on the nitrogen. So those substituents are added to the name as N, N dimethyl, and then we have 7 carbons in the parent chain, so it's heptanamide. In the next example, we have two different alkyl groups, a propyl group and a methyl group. Just like any other substituent, we want to alphabetize these substituents. So methyl goes first. So N-methyl, N-propyl goes in front of the parent name. The parent name is derived from having 6 carbons, includes a double bond on carbon 3, and of course the amide. So this parent name would be hex to indicate there are 6 carbons, 3-ene to indicate there's a double bond on carbon 3, and then finally amide. Note that we don't need to say where the amide is located since it's assumed to be on carbon 1. We have also stereochemistry for the double bond, which is E. You can confirm that by the fact that carbon 2 is going in the opposite direction as carbon 5. So the two largest groups around the double bond between carbon 3 and 4 are opposite to each other, so that would be E stereochemistry. This next example illustrates how you would treat a compound, an amide, that has both substituents on the nitrogen as well as somewhere on the carbon chain of the parent name. So we basically treat the three different substituents the same way, other than we use the letter N to indicate the location of the groups on the nitrogen versus a number to indicate the location of a substituent on the parent chain. So we are going to alphabetize these groups the same way, whether they're on the nitrogen or they're not. So in this example, we have an ethyl group. So that goes before methyl. So as far as the substituent, we would name this as N-ethyl, and then N-3 dimethyl. So N and 3 say that we have a methyl and methyl on carbon 3 as well as on the nitrogen. And lastly, the parent name of this compound has 5 carbons, so this is named as a pentanamide. Last thing is we have an example here where we have a propyl group and an ethyl group. We also have a methyl group on carbon 3. So we indicate where the substituents are with the locant. The N-ethyl tells us we have a nitrogen with an ethyl group, a nitrogen on the amide with an ethyl group. We also have a methyl substituent on carbon 3. And then we have a propyl group on the nitrogen as well. So notice we alphabetize the 3 substituents, whether they are on the nitrogen or somewhere on the parent chain. It does not matter. We alphabetize them and treat them the same way. Lastly, we have 4 carbons in the parent name or the parent chain. So this is a butanamide. With this question, we're going to review one of the examples of naming acid derivatives. So we want to draw the structure of a 4-methyl pentanoyl chloride, which is an acid chloride. To draw this acid chloride, we want to sort of break this name down. We have a pentanoyl chloride, which means an acid chloride, which has 5 carbons. So carbon 1 on the carbonyl, carbon 2, the CH2, another CH2, another carbon, and then a CH3. So 5 carbons in the parent name. We have also a substituent on carbon 4, which is a methyl group. So the carbonyl is carbon 1, and counting down, this carbon here is carbon 4, which has a methyl group. So this is the structure that we're looking for. For most of the chapter, we're going to cover a reaction called nucleophilic acyl substitution. So we're going to start by looking at the general reaction, the general mechanism for this reaction. So carboxylic acid derivatives have an acyl carbon that has some sort of leaving group, which we're going to abbreviate with the letter Y, that can be replaced by a nucleophile. This reaction has some similarities to nucleophilic addition reactions, which we covered earlier this semester. Nucleophilic addition reactions is a reaction that occurs with ketones and aldehydes, where a nucleophile adds to the carbonyl carbon. It breaks the double bond of the carbonyl to give us an alkoxide intermediate. So alkoxide means we have a negative charge on the oxygen. We sometimes refer to this intermediate as a tetrahedral intermediate. So it's tetrahedral at the center. At this point, for most nucleophilic addition reactions, this oxygen will react with aqueous acid to give us the final product, which has an alcohol and some sort of nucleophile added to the same carbon. So overall, this is a nucleophilic addition because we're adding a nucleophile to the carbonyl. Now, in this chapter, we're going to look at acyl substitutions, which involve typically an acid derivative. The difference between the acid derivatives and ketones and aldehyde is that the R group here, R prime specifically, is either an alkyl if it's a ketone or a hydrogen if it's an aldehyde. Both of those are very poor leaving groups. So when we get to the tetrahedral intermediate, there is nothing else to do for this intermediate other than getting rid of this negative charge by protonating the oxygen. However, when we get to a carboxylic acid derivative, this Y group differs a lot from an alkyl or a hydrogen. So typically, this Y group is a decent enough leaving group that when we get to the alkoxide intermediate, we can do an elimination instead. So the reaction starts the same way as nucleophilic addition reactions. So a nucleophile adds to the carbonyl, breaks the double bond to get to the alkoxide intermediate, or what we call the tetrahedral intermediate. Then this alkoxide intermediate will reform the carbonyl by eliminating whatever the leaving group is on the acid derivative. And therefore, as a result, this reaction is a substitution reaction where the nucleophile is replacing whatever the leaving group is on the acid derivative. Let's take a look now at the differences in reactivity between different acid derivatives and also compare them to aldehydes and ketones. So in general, amides are the least reactive acid derivative towards nucleophiles. Esters are next, so they are quite unreactive compared to other acid derivatives, but not as much as amides. Acid anhydrides are even more reactive. Acid chlorides are even more so. Now, if you're wondering, acid bromides are even more reactive. Now, we're not going to see too many examples because acid bromides are so reactive that they're sometimes very difficult to work with. Carboxylic acids, if you're wondering, depends on the reaction, but they're somewhere between an ester and an amide. So sometimes they're put around where the ester is. Sometimes they're put a little bit less reactive. It kind of depends on the reaction conditions. Aldehydes and ketones, as we just learned, They don't undergo acyl substitution, so with nucleophiles they do an addition reaction instead. But as far as reactivity towards nucleophiles, aldehydes and ketones are somewhere in here. They're not as reactive as an acid anhydride, but they're less reactive than esters. And between aldehydes and ketones, aldehydes are generally more reactive than ketones. Now, the trend that we observe on this chart here is due primarily to how good of a leaving group we have. So generally, the acid, bromide, and chloride have really great leaving groups. Then anhydrides have a pretty decent leaving group. Esters, they don't have as good of a leaving group. And amides have the worst leaving group from the acid derivatives shown here. The leaving groups, how good of a leaving group it is, depends on a few factors. For example, the electronegativity of the atoms that is attached to the carbonyl. It has to do also with the resonance stabilization of a negative charge. So in the case of anhydride, the leaving group is this essentially a carboxylate group, which has a negative charge on this oxygen once it's kicked out, which can be resonance stabilized. So for that reason, anhydrides are a little bit better. They have a better leaving group than the esters. The chlorides and the bromides, they have halogens, which they don't bond or they don't form a very strong bond to carbon because the orbitals of chlorine and bromine are slightly different sizes than the orbitals on carbon, so they don't overlap very well, and so they tend to form a very weak bond. Chlorine and bromine also are fairly electronegative, so they make for great leaving groups. And there's a few other reasons. Sometimes we use the explanation that the nitrogen, for example, can resonance stabilize into this carbonyl, so it makes that bond really strong. There are many reasons we sort of explain the trend we see here. The acid derivatives can be interchanged between so from one acid derivative to another fairly easily. It is even easier when you start off with a more reactive acid uh, derivative in converting it to a more or a less reactive one is a lot easier to do. So if we start off with an acid chloride, it's a lot easier to convert it into an anhydride, and the rest of the other acid derivatives is a lot harder to go from an amide to the rest. Although some reactions are possible to go the other way around, but in general, it's a lot easier to go from the anhydrides and the chlorides to the other acid derivatives rather than the other way around. There are other factors that will influence the reactivity of a particular carbonyl compound. For example, using an acid, whether it's a Bronsted or a Lewis acid, will help to quote unquote activate the carbonyl and make it more electrophilic and therefore more reactive towards nucleophiles. So if you have one of the acid derivatives like an amide or an ester, which are generally considered less reactive, we can still get them to react if we activate the carbonyl first by using a Lewis acid or a Bronsted acid. So in general, a Lewis acid or Bronsted acid will bond to the carbonyl oxygen and form an intermediate like this that has a positive charge on the on the oxygen. That makes this carbon of the carbonyl more electrophilic than without that activation, that bond to the Bronsted or the Lewis acid. Sterics also plays a role in the reactivity of different carbonyl or acid derivatives. So if we have several alkyl groups that are fairly bulky near the carbonyl, that will make the carbonyl carbon less reactive towards nucleophiles. So having several hydrogens in this alpha carbon means this carbonyl is more reactive towards nucleophiles than having several alkyl groups on that same alpha carbon. In this chapter, we're going to spend most of our time looking at conversion between carboxylic acids and other acid derivatives through nucleophilic acyl substitution. And we're also going to look at the interconversion of different acid derivatives as well through the same nucleophilic acyl substitution reaction. But we're also going to quickly look at reductions of carboxylic acids, deprotonation of a carboxylic acid with base, and then in the next chapter, we're going to look at alpha substitution of not only carboxylic acids, but acid derivatives as well. You might recall that alcohols will react with thionyl chloride to make an alkyl chloride. So this is a reaction we saw earlier this semester. We can also convert the hydroxyl group of a carboxylic acid with thionyl chloride into an acid chloride. Here's a second example with this benzoic acid derivative. If we add thionyl chloride, we can convert it into an acid chloride. Here's another example with acetic acid. If we add thionyl chloride, it will be converted into this acid chloride product here. Now the mechanism starts off with the oxygen of the hydroxyl group pushing electrons towards the carbonyl, and then the oxygen of the carbonyl will attack the sulfur, eliminate the chlorine, and form a bond between the oxygen and sulfur. We have this protonated carbonyl now on this side of the molecule. So base such as water or the chloride that got eliminated can remove this hydrogen, get rid of the positive charge, give us now what's called a chlorosulfite intermediate. This chlorosulfite, note that essentially what we have done is we have replaced the OH group of the carboxylic acid into a better leaving group, which is this chlorosulfite. The chlorine from the thionyl chloride that was eliminated in the first step can now add to this carbon, break the double bond. Then the tetrahedral intermediate can reform the carbonyl by eliminating this leaving group. Note that this step is an acyl substitution. So addition of a nucleophile to the carbonyl, and then the tetrahedral intermediate will lead to breaking down, forming the carbonyl, eliminating the leaving group, and as a result, we end up with the acid chloride. Now, in the first step of this mechanism, we saw that it was the oxygen of the carbonyl that actually attacked as a nucleophile this thionyl chloride, the electrophile. We're going to see this several times this chapter. So in general, between the two oxygens on a carboxylic acid or any acid derivative like an ester, the carbonyl oxygen is usually more nucleophilic than this oxygen here. And one way of thinking about this is if we push electrons, the lone pair on this oxygen towards the carbonyl, we have this other resonance form that has a negative charge on this oxygen. So in general, the oxygen of the carbonyl is more nucleophilic than the other oxygen on this carboxylic acid. Earlier this semester, we talked about a reaction that converts alcohols into alkyl bromides. We can use for this transformation a reagent called phosphorus tribromide. Very similarly, we can convert a carboxylic acid into an acid bromide by using phosphorus tribromide. Benzoic acid can also be converted into benzoyl bromide by using phosphorus tribromide. Here's one more example with acetic acid. If we add PBr3, it will be converted into acetyl bromide. The mechanism is pretty similar to what we saw with thionyl chloride. So it starts off with the lone pair on this OH oxygen, pushing electrons towards the carbonyl. The carbonyl oxygen then attacks the electrophile, which is this phosphorus, and eliminates one of the halogens on the phosphorus. That gets us to this intermediate. Base removes a proton to give us the key intermediate in this mechanism is called a dibromophosphite. Notice that we have turned the OH group into a intermediate that has a good leaving group. And now Br negative, which is the bromine that was eliminated in the first step, can add to the carbonyl carbon, break the double bond. We get to a tetrahedral intermediate, which then reforms the carbonyl, eliminates the leaving group to give us this acid bromide. Notice that the last two steps is an acyl substitution, where bromine is the nucleophile and adds to this acid derivative and replaces the leaving group. Carboxylic acids can be converted into esters a number of ways. One of those is by reaction with an alkyl halide. You might recall a reaction earlier this semester called the Williamson ether synthesis, which involves starting with an alcohol, adding base, such as sodium hydroxide or sodium hydride, followed by an alkylating agent like methyl bromide. The base removes the proton on the alcohol, and then the oxygen is more nucleophilic and therefore attacks this electrophile, eliminating the bromine. As a result, we get an SN2 reaction and we end up with an ether. We have essentially replaced the hydrogen on the alcohol with a methyl group. We could do a similar reaction with carboxylic acids that replaces the hydrogen on the carboxylic acid with an alkyl group. So adding sodium hydroxide or sodium hydride followed by an alkylating agent will lead us to an ester. The base removes the proton on the carboxylic acid to give us a conjugate base. This is now more nucleophilic than the carboxylic acid, so this oxygen can now attack a carbon that has a leaving group to do an SN2 reaction, and we end up with an ester. Since this is an SN2 reaction, just like the Williamson ether synthesis, it's best to use unhindered alkyl halides. So primary alkyl halides are best for this, or even methyl halides. In the cases of acetate nucleophiles, they are not very basic, so you can also do SN2 reactions with secondary alkyl halides pretty well. Here's another example with benzoic acid. If we add base, you will get the conjugate base of this carboxylic acid, which is more nucleophilic, and so this oxygen will now add to this secondary carbon and do an SN2 reaction. Now, since it is an SN2 reaction, we're going to get a inversion of stereochemistry in the product, which we see here. Classic reaction in organic chemistry is the Fischer esterification reaction. This is a reaction where a carboxylic acid, such as benzoic acid, reacts with an alcohol. In this example, we're using ethanol. The reaction is typically done under acidic conditions with an acid catalyst such as Acyl, and the reaction leads to an ester product, in this case ethyl benzoate, and then a water molecule as a byproduct. Now this reaction is reversible, and so anytime we have an ester and we add water and an acid catalyst, we can usually reverse the reaction and go back to the carboxylic acid and the alcohol. Since this is a reversible reaction, we can use Le Chatelier's principle to shift the equilibrium one way or the other. For example, using an excess of alcohol or carboxylic acid, will push the reaction towards product. Removing one of the products, for example, removing the water through distillation or some sort of drying agent that soaks up the water, will also push the reaction towards product. As mentioned before, we can push the reaction towards the carboxylic acid by adding water in excess, or adding, and generally this wouldn't be practical, but you could, I guess, theoretically add an excess of the ester as well to push the reaction towards the reactant. You could also remove an alcohol from the reaction through distillation. So again, that would push the reaction towards the left side of this reaction. Here's another example with this propanoic acid and isopropanol. If we use Acyl as a catalyst, we can make an ester, which is shown here, plus a water molecule. Here's the mechanism for the Fischer esterification reaction. It starts off with a carboxylic acid being protonated by Acyl or other acid catalyst. Then water will add to the carbonyl of the carboxylic acid, breaking the double bond, leading to this intermediate, which then loses a proton. So although not shown here, another water molecule can come along and pick up this hydrogen. So that would occur as follows. So either water or some other base in the reaction can pick up this proton, break that bond, give those electrons to the oxygen, get rid of the positive charge on the oxygen, and that leads us to this tetrahedral intermediate. In the next step, water will remove this proton, form a carbonyl by eliminating the leaving group. Now notice the OH is now protonated, so that's a step that actually occurs before the elimination. So a hydronium ion can do this in the previous step. So this oxygen can pick up a proton from the hydronium ion, and that hydronium ion can form from HCl reacting with water, for example. You have now a better leaving group here, and so when the water removes this proton, we can easily eliminate that hydroxyl group that is protonated. That essentially leads us to the final product, which is the ester. So overall, we have replaced a hydroxyl group with an alkoxide group by this acid catalyzed acyl substitution. There's a third method that is used to make esters from carboxylic acids. That involves using a reagent called dicyclohexylcarbodiamide, which is abbreviated as DCC. So this is an alternative to the Fischer esterification. It avoids having to use an excess of alcohol or carboxylic acid, which we usually use in the Fischer esterification to push the reaction towards products. With DCC, we can use one equivalent of an alcohol, one equivalent of a carboxylic acid, and DCC will join them together into an ester. And then there will be a byproduct called DCU, which stands for dicyclohexylurea. This is the structure of DCC. You don't need to memorize it. It's what we call a carbodiamide. Essentially, is two imine groups attached to the same carbon. Here's another example of this reaction with benzoic acid and ethanol. DCC will join them to make ethyl benzoate plus a byproduct of DCU. Here's another example of this DCC promoted reaction involving acetic acid and methanol to make methyl acetate. and then there's also a DCU byproduct. The mechanism for this reaction is as follows. So the DCC has a couple of nitrogens which can act as bases. One of those nitrogens will pick up a proton from acetic acid and form the conjugate base, which is the acetate ion. That also gives you a DCC molecule that's protonated. This acetate ion is now more nucleophilic. This carbon is now more electrophilic. So the acetate ion attacks the carbon, breaks this double bond. They're joined together now. And then in the next step, we're going to do an acyl substitution where the alcohol adds to the carbonyl, breaks the double bond. We get a tetrahedral intermediate. And then that tetrahedral intermediate breaks down to reform the carbonyl and eliminate the leaving group, as shown here. As a result, we get the ester, and we get this DCU byproduct. In this question, we want to try to attempt to prepare the following ester with a corresponding carboxylic acid. So in this question, we want to make the following ester from a carboxylic acid. In this chapter, we looked at 3 different reactions that can do this. So one of them was the Fischer esterification. The other one was with DCC. And then the first one we looked at was taking a carboxylic acid, adding base and an alkyl group through an alkylation reaction. We can pretty much use any of the 3 reactions in this example, since the reaction or the question is not very specific. For example, we could use the Fischer esterification. If we look at our ester and imagine breaking it here, the left side would be carboxylic acid, the right side would be an alcohol, so methanol from the right side, and then butanoic acid from the left side. So butanoic acid plus methanol plus Acyl through a Fischer esterification will lead us to that ester. It will be a water molecule as a byproduct. Alternatively, we can use DCC for the same reaction. So we could use the same 2 reactants plus DCC, and it'll make that ester. And a third reaction would involve, instead of using methanol, we would use an alkyl halide, for example, methyl bromide. We would also use a base. So for example, sodium hydroxide. So that would be step 1. And then step 2 would be this methyl bromide, and we could get to that same ester. Carboxylic acids can be converted into amides, sometimes simply by heating a carboxylic acid with the appropriate amine. For example, ethylamine, as shown here, can be mixed with propanoic acid, heated to be converted into this amide. A water byproduct will also result. Now, the reason why this reaction is relatively slow and the reason we need to heat it is because when you mix an amine, which is basic, and a carboxylic acid, which is acidic, the first thing that's going to happen is the nitrogen will deprotonate the carboxylic acid, and you get these 2 byproducts, an acetate ion and an ammonium ion. If we heat these 2, then we can get the nitrogen to attack the carbonyl and replace the hydroxyl group on it, and you get a substitution reaction. Now the problem with this step is, or this route is, that our electrophile is negatively charged and our nucleophile has a positive charge. So this is the reverse of what we want typically for a substitution reaction to occur. So for that reason, we have to heat this reaction, and sometimes to quite high temperatures. Now, a much easier way, and usually the way that we try to do this conversion, is by taking a carboxylic acid and an amine, and instead of heating it using DCC. DCC will convert an amine and a carboxylic acid into an amide, and there will be a byproduct of DCU. Note that this reaction we saw earlier, a similar example with esters. So we could use an alcohol and a carboxylic acid to make esters with DCC. This reaction has traditionally been used to make peptides. So amino acids can be joined with DCC. You might recall that amino acids have a carboxylic acid and an amino group on the same carbon. And then they also often have some sort of side group that differs depending on the amino acid. By joining two amino acids, by reacting a carboxylic acid from one and an amino group from the other, we can make an amide bond as shown here, and as a result we get a dipeptide. Now we can repeat this process multiple times and grow this chain and make a fairly large peptide. In fact, this reaction is so simple that automation has been added to it. There are certain instruments that are used to make large peptides by taking different amino acids in a sequence that you input into the instrument. The instrument will mix different amino acids in the appropriate sequence, adding DCC each step, and then washing the peptide that results, and then adding the next amino acid that needs to be added on the peptide plus DCC to repeat the process and grow a chain in an automatic way. Here is a look at the mechanism for the DCC promoted reaction between carboxylic acids and amines. It starts off with the DCC, the nitrogen on the DCC, deprotonating a carboxylic acid, giving you the conjugate base, which is now more nucleophilic and able to attack this carbon of the protonated DCC, breaking the double bond here. Now they're joined together in the next intermediate. The amine will add to the carbonyl carbon through an acyl substitution, break this bond here. And then in the next step, which we see here, we can reform that carbonyl by eliminating the leaving group and therefore forming DCU plus the amide. Anhydrides traditionally are made by heating two molecules of a carboxylic acid to make a symmetrical anhydride. Now this reaction has been used for many years to make industrially acid anhydrides. Now this reaction for the most part is not practical for most acid anhydrides, so there are better ways to make them, at least on a smaller scale in a lab. Also, note that this reaction where we heat two molecules of a carboxylic acid always produces a symmetrical anhydride. So if you wanted an unsymmetrical anhydride, you have to use a different method. So an alternative method to make anhydrides is from an acid chloride. So if we take a carboxylic acid and we add base, we will deprotonate this hydrogen, make that oxygen more nucleophilic. That oxygen can now attack an acid chloride, do an acyl substitution, and eliminate this chlorine. And so now the oxygen will be bonded to the carbonyl, and you therefore form a anhydride as a result. Now this example I'm showing leads to a symmetrical anhydride, but if we use a different acid chloride with a different alkyl group than the carboxylic acid here, you don't necessarily have to form a symmetrical anhydride. Here's another example of making an anhydride from a carboxylic acid and an acid chloride. So if we add base, we will remove the acidic proton on the carboxylic acid. That leads us to this conjugate base. which is more nucleophilic since it has a negative charge on the oxygen. That oxygen can attack an acid anhydride, break the double bond, give us a tetrahedral intermediate. The tetrahedral intermediate will reform the carbonyl by eliminating the leaving group, which is the chlorine, and that gives us the anhydride. Now notice this anhydride is unsymmetrical since the alkyl groups on the carboxylic acid is different from the acid anhydride. As we saw earlier this semester, carboxylic acids can be converted into alcohols by a reduction reaction with lithium aluminum hydride. We start off with this carboxylic acid, we add lithium aluminum hydride, followed by aqueous acid. We can convert it into a primary alcohol. The reaction starts by the hydride on lithium aluminum hydride, adding to the carbon of the carbonyl here, breaking the double bond, then reforming the carbonyl and eliminating the OH group to give you an aldehyde. Now this intermediate is not really isolated. Aldehydes, as we know, can also react with lithium aluminum hydride, and so another equivalent of lithium aluminum hydride will add to this aldehyde carbon to give you an alkoxide ion. This won't react any further until we add aqueous acid, so the oxygen will be protonated by the acid and give you a primary alcohol. Note that other hydride reagents such as sodium borohydride or dibol are not able to do this type of reaction. In this section, we're going to look at how acid derivatives can be converted into other acid derivatives by the appropriate reaction. For example, if we add water to any acid derivative, we can turn it into a carboxylic acid. If we add an alcohol, we can turn it into an ester. If we add an amine or ammonia, we can convert it into an amide. We'll also look at reactions with nucleophiles such as a Grignard, which will convert an acid derivative generally into a ketone initially, and then into a tertiary alcohol, after the reaction occurs again. Acid derivatives can also react with hydrides to be converted into aldehydes, which generally will be reduced further into an alcohol. Okay. We're going to look at a number of acyl substitution reactions. It's important to remember that in acyl substitutions, a nucleophile is replacing the leaving group. And so you should be able to recognize this pattern and be able to predict the product once you know which nucleophile you're using. And it doesn't matter which acid derivative we're using, since the product will be the same and be primarily based on the nucleophile we're using. The leaving group will then be eliminated as a byproduct, and so the byproduct will always be dependent on whichever leaving group we have on the acid derivative. So keep that in mind as we go through these many examples so that you're not overwhelmed as far as predicting the product from each reaction. We're going to start off with hydrolysis reactions, meaning the addition of water to different acid derivatives. And we're going to do this in a sequence where we start with the most reactive acid derivative, which is the acid halides. An acid chloride, for example, can react with water to become a carboxylic acid. So the water will add to this carbonyl and kick out the chlorine, and so you'll have a hydroxyl group there and therefore form a carboxylic acid. As a byproduct, the chlorine will become ACl. Here's a look at the mechanism. Water can add to the carbonyl, break the double bond, give us a tetrahedral intermediate, which then reforms the carbonyl, eliminates the leaving group to give us this protonated carboxylic acid, which then loses a proton with base to become a carboxylic acid. Acid chlorides and even acid bromides are so reactive that this reaction can be done under neutral conditions. So water, although it's not the greatest nucleophile, it's a good enough nucleophile to react with this very hot electrophile. Acid anhydrides are very reactive, not quite as reactive as an acid chloride or an acid bromide, but they're quite reactive enough that they can react directly with water without the need of heating or an acid catalyst, for example. So water can add to an acid anhydride. So the water would add to one of these two carbonyls, and it doesn't matter which one you pick first. It will lead to an acyl substitution that turns these anhydrides into two carboxylic acids. So if you break the anhydride in half, you'll turn the left side into a carboxylic acid, the right side into a carboxylic acid, and so you'll have benzoic acid and acetic acid. Note that this reaction is the reverse of the reaction we saw earlier, where we took two molecules of a carboxylic acid or two different molecules, and if we heated them, we would get an anhydride plus a water byproduct. Here's a look at the mechanism for this reaction. So water adds to one of the two carbonyls, and again, it doesn't matter which one. It will give us a tetrahedral intermediate. Water or some other base will remove one of these protons from the water they just added, giving us this product or this intermediate. The oxygen of what used to be the carbonyl will reform the carbonyl, eliminate the leaving group, and give us the two carboxylic acids. Now, esters and amides are less reactive than anhydrides, and so to hydrolyze esters and amides, we need to typically step up our reaction. We need to either heat the reaction or use an acid catalyst or do both. An ester can be hydrolyzed under acidic conditions. So if we add water to an ester, an ACl, we can hydrolyze this ester bond and turn the carbonyl into a carboxylic acid, and the alkoxide group here on the ester is eliminated as an alcohol. Now notice this reaction is the reverse of the Fischer esterification reaction. In the Fischer esterification, we started with a carboxylic acid and an alcohol, added ACl to get an ester and a byproduct of water. Here's another example. Here is ethyl benzoate. If we add water and ACl, we can hydrolyze that ester into a carboxylic acid and ethanol. Let's take a look now at the mechanism for the acid catalyzed ester hydrolysis. Starting off with an ester, if we add an acid catalyst, or if you want to use the hydronium ion, which is the result from an acid reacting with water, either way, we can protonate the carbonyl. We now have a protonated carbonyl in the next intermediate. It's a better electrophile than the ester we started with. Water can then add to the carbonyl, break the double bond, give us this tetrahedral intermediate, and then water can remove this proton, form a double bond, a carbonyl, by eliminating the leaving group. That gives us the carboxylic acid, an alcohol, and then a byproduct of the hydronium ion, which starts the cycle once again. So this is our acid catalyst in this mechanism, and it starts the cycle again. Amides are the least reactive acid derivative that we'll talk about in this chapter. And amides in general, in order to be hydrolyzed, need to be not only treated with an acid or a base catalyst, we also usually have to heat the reaction as well. Here's an example with an amide. If we add water and HCl, we have to heat it to hydrolyze that amide into a carboxylic acid and an amine. The amine comes from the leaving group on the amide. The carboxylic acid comes from the water adding and replacing the amine leaving group on this carbonyl. Here's another example. Another amide is hydrolyzed with water and Acyl by heating. It is turned into a carboxylic acid and the appropriate amine. The mechanism for this reaction starts by the carbonyl of the amide being protonated. Then water adds to the carbon of the carbonyl, breaks the double bond, gives us a tetrahedral intermediate, which then loses a proton, as shown here. So water removes this proton, forms a carbonyl, eliminates the leaving group. It gives us a carboxylic acid plus an amine, or in this case, an ammonia molecule as a byproduct. Esters and amides can also be hydrolyzed under basic conditions. And we're going to refer to this reaction as a base-promoted reaction because the base is actually consumed in the reaction and it is not acting as a typical catalyst, which is regenerated. So under acidic conditions, the acid is a catalyst. Under basic conditions for hydrolysis of esters and amides, the base is actually consumed, and so we consider that a base-promoted reaction. Starting off with the ester hydrolysis, under basic conditions, we would use sodium hydroxide or some other base plus water. And then since the reaction leads to a carboxylic acid, which is acidic, and we're using basic conditions, we have to use a second step, which involves a small amount of acid that neutralizes the base plus protonates this carboxylic acid. And so anytime any reaction leads to a carboxylic acid as a product and the reaction is done on the basic conditions, we always have to use the second step of acid. So this reaction not only produces a carboxylic acid, but also an alcohol. So the alkoxide group on the ester is eliminated as an alcohol, so we get ethanol in this example. Here's one more example. Under basic conditions, the water will add to this carbonyl and turn it into a carboxylic acid, which is shown here. And then the leaving group becomes an alcohol. So this is propanol that's eliminated, and you see that in the product. Here's a look at the mechanism for ester hydrolysis under basic conditions. So the hydroxide ion is a very good nucleophile. So unlike water, when we add water to an ester, we have to protonate it first, since water is a poor nucleophile. But the hydroxide ion is a very strong nucleophile, so it can add directly to the carbon. It breaks the double bond, gives us this intermediate, this tetrahedral intermediate. The carbonyl reforms by eliminating the leaving group, the alkoxide group on the ester. We end up with a carboxylic acid initially. We get a leaving group here, which is an alkoxide ion. Now, because the reaction is done under basic conditions, usually this carboxylic acid is deprotonated. It turns into the conjugate base. And so we have to use aqueous acid in the last step to return back to the carboxylic acid. Amides can be hydrolyzed under basic conditions as well. Typically, this reaction is done by heating the reaction, since amides are relatively unreactive compared to other acid derivatives. So as an example, if we take this amide, we can hydrolyze it with sodium hydroxide, water, by heating. So this carbonyl becomes a carboxylic acid, which is propanoic acid. The amine leaving group is eliminated as an amine, so we end up with a primary amine. Now notice this reaction has a second step of aqueous acid. The reason for that is Since we're producing a carboxylic acid, which is acidic, and we're doing it under basic conditions, we have to use aqueous acid at the end to neutralize the base, plus turn the conjugate base of the carboxylic acid into a carboxylic acid. Here's a look at the mechanism. Starts off with the hydroxide ion attacking the carbonyl carbon, breaking the double bond here, giving us a tetrahedral intermediate. The carbonyl reforms by eliminating the amino group. That gives us initially a carboxylic acid, but because this is done under basic conditions, the carboxylic acid is deprotonated and turned into a carboxylate ion. For this reason, we have to use aqueous acid as a second step to add a proton back on the carboxylate and end up with a carboxylic acid at the end of the reaction. Earlier in this chapter, we saw a reaction involving ester hydrolysis under basic conditions to make a carboxylate ion, and then if we added aqueous acid as a second step, we would make a carboxylic acid. Now that reaction is often referred to as a saponification reaction because the reaction is traditionally used to make soaps. So soaps are made by taking a fat, which is essentially a triglyceride. So triglycerides are made from taking 3 fatty acids or perhaps 2 fatty acids and a phosphatate group attached to a triglycerol molecule. So triglycerol has 3 carbons and 3 alcohols on those carbons. If we add sodium hydroxide or potassium hydroxide, we can hydrolyze these esters, as we've seen before, into an alcohol, or actually a triol, and 3 molecules of these carboxylates. Since the esters here are formed from fatty acids, so triglycerides involve 3 fatty acids, or sometimes 2, the product that we get here would be the conjugate base of a fatty acid. So soap is simply a sodium or potassium salt of a fatty acid. And again, that's typically made from taking a triglyceride and adding a base plus water and hydrolyzing the ester bonds. An example of a soap molecule would be sodium stearate, which is the sodium salt of a fatty acid. Now, there are many soaps that are sold commercially, and each one will have different properties. Some are liquids, some are solids. They'll be a little bit more slimy than others. All of that depends a lot on the molecule that we make it from. So the triglyceride source will give you different salt properties. Also using sodium versus potassium hydroxide will give you slightly different properties for the soap that we make at the end of the reaction. We're going to try to convert N-ethylbenzamide into benzoic acid. Amides can be converted into carboxylic acids through a hydrolysis reaction. The hydrolysis reaction of amides always has to include an acid or a base catalyst, and it has to be heated. So as an example, we can convert N-ethylbenzamide into benzoic acid by adding Acyl, water, and heat to do the hydrolysis reaction. A second way we can do this reaction would be under basic conditions. So for example, we could use sodium hydroxide, water, and heat. Now, any reaction that leads to a carboxylic acid and is done under basic conditions has to involve a second step where we add a little bit of acid. So we could abbreviate that by just simply add hydronium ion. The hydronium ion would neutralize the sodium hydroxide. It would also convert the conjugate base of the carboxylic acid into a carboxylic acid. So there's two ways you can do this hydrolysis reactions, as you see here, under acidic or basic conditions. Derivatives will react with alcohols to make esters. For example, an acid chloride, which is very reactive, can react with an alcohol at room temperature to produce an ester. In this example, notice we're using pyridine. The role of pyridine here is to soak up or react with the Acyl byproduct of the reaction. Since we're using an acid chloride, that chlorine eventually picks up a proton and becomes Acyl. In the second example, we're using a diol. The diol has a primary alcohol and a secondary alcohol. Primary alcohols in general are more nucleophilic than secondary alcohols since they're less hindered. And so if we were to use one equivalent of an acid chloride or any other acid derivative, the reaction will occur through the primary alcohol. So as this example illustrates, we form an ester from the primary alcohol, and notice the secondary alcohol doesn't react. Now, if we use enough acid chloride, the secondary alcohol will become an ester as well. Alcohols can react with acid anhydrides to be converted into esters. As an example, we have here a primary alcohol mixed with acetic anhydride and a small amount of pyridine. The pyridine helps to remove the proton on the alcohol and make it more nucleophilic, and as a result we get an ester. Now notice half of the acetic anhydride will be eliminated as a carboxylic acid or acetic acid in this example. In the next example, we have a diol involving a primary alcohol and a secondary alcohol. When we use only one equivalent of the acid anhydride, only the primary alcohol is converted into an ester since it's more nucleophilic. The other half of the anhydride will become a carboxylic acid. The secondary alcohol will remain unreacted, and if we were to use enough of the anhydride, 2 equivalents or more, we can convert that secondary alcohol into an ester as well. Alcohols are more nucleophilic than the carboxylic acid hydroxyl group. And so in this example, if we use an acetic anhydride, only the alcohol is converted into an ester. As a side note, esters are sometimes used as protecting groups for alcohols. Addition of an alcohol to an ester can lead to a reaction called transesterification, which is the conversion of one ester into another type of ester. As an example, if we start off with ethyl propanoate and we add HCl and methanol, we can exchange the alkoxy groups on the ester into a different one, in this case methoxy. So the methanol will add and replace the alkoxy group already on the ester. Now notice this reaction is done under acidic conditions, so that's typical for transesterifications. Since esters are relatively unreactive, unlike acid chlorides and acid anhydrides, which can react at fairly neutral pH with an alcohol, esters require usually mild heating and usually an acid catalyst or a base catalyst for the reaction. Here's an example of an intramolecular transesterification. If we have a molecule that has an alcohol and an ester, we can add HCl to help the reaction. So the HCl will protonate the carbonyl that would allow the alcohol to attack the ester and cyclize this molecule and give you a cyclic ester, which we refer sometimes as a lactone. The alkoxy group, which in this case is a methoxy group, will be eliminated as an alcohol, a methanol molecule. Also do a transesterification reaction under basic conditions. This is referred to as a base-promoted reaction since the base is generally used up in the reaction and it's not your traditional catalyst. Whatever alcohol we want to add to the ester, we typically take the conjugate base and use that as a base. So for example, if we wanted to add methanol to this ester, we would use the conjugate base of methanol, which would be a methoxy group, to act as the base. Just like the acid catalyzed reaction, we want to heat this reaction since esters are relatively unreactive. And notice in this reaction, we're changing the ethoxy group for a methoxy group, therefore doing a transesterification reaction. The ethoxy group, which is eliminated as an alcohol. So in this case, we get an ethanol molecule. Here's an example of an intramolecular reaction between an alcohol and an ester. So the alcohol will cyclize on this ester and form a cyclic ester, a lactone. Aspirin, as we probably know, is an anti-inflammatory and fever-reducing drug. It was originally isolated from the bark of the willow tree, and nowadays is typically made in a lab. Now, aspirin is responsible for increasing or reducing inflammation and reducing fever by inhibiting the action of an enzyme called cyclooxygenase, which is usually abbreviated as COX or COX enzyme. The way that aspirin inhibits the COX enzyme is by transferring an acetyl group to the serine amino acid and found in the active site of this enzyme. So a serine group has a primary alcohol as a side group, and aspirin looks or has a structure like this, which includes an acetyl group or an ester group. The alcohol, the primary alcohol from the serine group from the COX enzyme will attack the acetyl group of aspirin and essentially do a transesterification reaction to transfer the acetyl group onto the serine. This inhibits the action of this enzyme and therefore leads to the reduction of inflammation as well as the reduction in fever. There's an enzyme in our bodies called pancreatic lipase, which is responsible for breaking down triglycerides into fatty acids, as well as a monoacylglycerol molecule. Now, this pancreatic lipase has a serine group in its active site containing an alcohol that is nucleophilic, and certain anti-obesity drugs such as orlistat are composed of a beta-lactone, which is a cyclic ester containing 2 carbons in addition to the ester group. This is a very reactive ester, so most esters are relatively unreactive towards nucleophiles, but when you put the ester in a small ring, such as a 4-member ring, that ester behaves more like an acid chloride in terms of reactivity, and it will react with the serine group of pancreatic lipase and therefore inhibit the action of that enzyme. As a result, these anti-obesity drugs stop the breakdown of fatty acids, and triglycerides, instead of being digested, will simply go undigested to the digestive tract of a person. In this question, we want to look at the mechanism for the following nucleophilic acyl substitution reaction. So this reaction involves an acid chloride, a methoxy nucleophile in methanol to become an ester. This exact example was actually not covered in this section, but is one that we should be able to come up with a reasonable mechanism based on the other examples of acyl substitution reactions we saw in this chapter. So in this reaction, we're using a base to do an acyl substitution on an acid chloride. So the reaction should work by the base, the methoxy group, attacking the carbon of the carbonyl of the acid chloride, breaking the double bond to form a tetrahedral intermediate, and then the oxygen reforming the carbonyl by eliminating the leaving group. In this question, we have a functional group that we did not see in this chapter react with different nucleophiles. So this is a cyclic anhydride, and we want to react it with one equivalent of methanol. Now, we saw examples in this chapter of anhydrides reacting with methanol, so we should be able to come up with a reasonable product based on those examples. As we saw in some of the examples in this section, alcohols add to acid anhydrides by an acyl substitution. And so in this example, we have simply a cyclic anhydride. So we should see a similar reaction. If we use one equivalent of methanol, then the alcohol should add to one of these carbonyls, either one. In this case, it would not matter since the anhydride is symmetrical. And that would lead to breaking this oxygen bond here, so eliminating this, right? And half of the molecule, in this case the bottom half, would become a carboxylic acid. The top one would become an ester that involves the methanol being connected to a carbonyl. In this question, we want to predict the reactant, and specifically the acid chloride that we would need to use in order to make ethyl benzoate through an acyl substitution reaction. In a way, we also need to predict which alcohol we need to use as well. In order to make ethyl benzoate, we need to think about which acid chloride and which alcohol we need to use. In order to figure this out, we want to break this bond between the carbonyl and the ethoxy group and turn the carbonyl into an acid chloride, which would mean we would need to use benzoyl chloride. We would also need to convert this ethoxy group, the leaving group, into an alcohol that we would use as a nucleophile. And so the alcohol that we would need to use would be ethanol. Amines are fairly good nucleophiles that can react with different acid derivatives to make other acid derivatives, specifically amides. If we start off with an acid chloride and we add 2 equivalents of ammonia, we should make a primary amide. One of these ammonia molecules would replace the chlorine and give you an NH2 group on the carbonyl. The other molecule of ammonia will react with the ACl byproduct that results from any acyl substitutions on an acid chloride and would form a byproduct of ammonium chloride. In the next example, again, we're using an acid chloride, benzoyl chloride to be exact. We have to use 2 equivalents of an amine. One will replace the chlorine and give you, in this case, a tertiary amide. And the second molecule of the amine will react with Acyl to give you an ammonium byproduct. Note that we can use just about any amine or ammonia derivative in this acyl substitution, and any other acid derivative would work the same way. However, tertiary amines are not generally used for this reaction. In fact, they're usually not used as nucleophiles, since the nitrogen already contains 3 alkyl groups. It doesn't like to add to electrophiles, since it would lead to forming an ammonium product, which has 4 groups on nitrogen with a positive charge on the nitrogen. So generally, tertiary amines are not used as nucleophiles in not only acyl substitutions, but other types of reactions. As a side note, amides are sometimes used as protecting groups for certain amines. If we have a primary amine, we can react it with an acid anhydride, such as acetic anhydride, and form an amide, as well as a byproduct of a carboxylic acid. So half of the acid anhydride will be eliminated as a carboxylic acid after the nitrogen has attacked one of the carbonyls and eliminated that carboxylic acid. Note that amines are in general more nucleophilic than alcohols. So if you had a molecule that had both an amino group and an alcohol group, if we use only one equivalent of an acid derivative, whether it's an acid anhydride or an acid chloride, the reaction would always occur through the nitrogen. And so you can see that the product contains an amide bond rather than an ester bond. Now, if we use enough of the acetic anhydride or any other acid derivative, we could also form an ester from the alcohol. Esters can react with amines such as ammonia to form amides as well. Now, generally, esters are less reactive than acid anhydrides and acid chlorides, so we usually have to heat the reaction. And here's an example with methylbenzoate reacting with ammonia to form benzamide, as well as a methanol molecule byproduct. So the byproduct comes from the leaving group of the ester, and then the amide forms from the ammonia, adding to that carbonyl to give you this primary amide. Here's a second example with a primary amine. It replaces the ethoxy leaving group, which becomes an alcohol, ethanol. The amine, once it adds, it forms an amide, a secondary amide. This reaction could occur intermolecularly, and that would be true for any acid derivative. So the amine would add to the ester, eliminate the leaving group, which becomes a methanol molecule. In the process, we form, in this case, a 6-member cyclic amide. Cyclic amides are referred to sometimes as lactams. And lactams are actually very important in the chemistry of antibiotics. Specifically, many antibiotics, such as penicillin G, have a 4-member cyclic amide. This is called a beta-lactam, since it contains 2 carbons in addition to the amide. Beta-lactam antibiotics such as penicillin were among the earliest discovered antibiotics. Penicillins were originally discovered as from a mold growing on a cantaloupe back around the 1930s, and then it was developed into an antibiotic eventually in the 1940s. Antibiotics are one of the main reasons why the life expectancy of humans has drastically increased from the 1940s until now. Beta-lactam antibiotics work by inhibiting an enzyme called transpeptidase. which has a serine group with a hydroxyl group attached in the active site of this enzyme. Now, the enzyme is responsible for the synthesis of bacteria cell walls, and that serine group will generally react with the carbonyl of beta-lactam and connect to it through a ester bond, and therefore the enzyme is inhibited. Now, in general, amides are fairly unreactive, but when they're placed in a small ring like a beta-lactam, they tend to react more like an acid chloride, and so they're extremely reactive towards nucleophiles such as an alcohol. We want to prepare propanamide using an acid chloride and an amine or ammonia. So attempt to do this problem before you look at the next slide. So to answer this question, we want to convert propanamide into an acid chloride and amine. In order to do that, we should imagine replacing the amino group with a chlorine. That would give us propanoyl chloride. The amino group, in this case, is NH2. If we add a hydrogen, we come up with ammonia. So that would be the amine that we want to use. Carbanions such as Grignards and organolithiums add to acid derivatives such as an acid chloride to make tertiary alcohols. As an example, an ethyl organolithium will add to an acid chloride to add two ethyl groups and give you a tertiary alcohol. We could do the same thing with a methyl Grignard, which will add a methyl group to benzoyl chloride to initially give you a ketone. But as we know, ketones also react with Grignards and organolithiums. And so instead of isolating the ketone, typically we will get an alcohol, a tertiary alcohol as a product. Also react with Grignards and organolithiums to make tertiary alcohols. As an example, phenyl Grignard will add twice to methylbenzoate to give you triphenyl methanol. So two new phenyl rings are added to the carbon that used to be part of the ester. An organolithium will do the same thing to an ester to give you a tertiary alcohol that has two ethyl groups added. Organocuprates will add to acid chlorides, and instead of doing an addition, they do generally a substitution reaction. So an acid chloride as shown here will react with a Gilman reagent to make a ketone. Here's another example with an acid chloride. If we have a Gilman reagent that has a pair of ethyl groups, one of those ethyl groups will be transferred and the chlorine will be replaced by an ethyl group. In this last example, a Gilman reagent with methyl groups will substitute a chlorine on an acid chloride to give you a methyl ketone. Note that this reaction is specific to acid chlorides. Other acid derivatives like esters, amides do not undergo this type of reaction. In this question, we want to predict the ester that we would need to start with in order to do a Grignard reaction and make the following alcohol. To answer this question, we want to look at the alcohol that we're going to end up with and think about what ester and what Grignard reagent we would want to use. One of the things you might notice is that the alcohol we have here has two phenyl rings. You might recall that generally when we do a Grignard reaction on an acid derivative such as an ester, we generally add one alkyl group from the Grignard twice. And so the hint here is that this phenyl ring probably comes from the Grignard. And so we will use a phenyl Grignard reagent, 2 equivalents of it or more, and use an ester that has a methyl group as a substituent on the side of the carbonyl. So that means that we would have this ester, so a methyl attached to the carbonyl, and then some sort of leaving group on the ester. It doesn't matter what R group is on the oxygen, the reaction should work the same. And so these are the 2 components we would need to use in order to make the alcohol we started with. This question asks us to make the following ketone from an acid chloride and a lithium diorganocuprate reagent. Lithium diorganocuprates are Gilman reagents or copper reagents. And so let's think about what 2 components we would use to make the following ketone, and then we'll look at the answer on the next slide. In this question, we want to make a ketone from cuprate reaction on an acid chloride. This ketone is unsymmetrical. It has what looks like an isopropyl group on the right side. It has a phenyl ring on the left side. So we're looking at this ketone. And with the Gilman reagent in an acid chloride reaction, we have actually 2 options here. We can have the Gilman reagent provide the phenyl ring, or it can provide the isopropyl group, which means acid chloride can have already an existing phenyl ring or an isopropyl ring on it. And so the 2 possible answers are we use this acid chloride with a phenyl ring attached, and the isopropyl group will come from the Gilman reagent. Or we could exchange those 2 alkyl groups and provide the phenyl ring from the cuprate, and then the acid chloride already has the isopropyl group already attached. Acid derivatives react with hydride reagents, such as sodium borohydride, and they generally react twice with a hydride reagent. For example, this acid chloride would react with sodium borohydride, whose structure is shown here. One of the hydrides on the borohydride reagent would add to the carbonyl, break the double bond, give us a tetrahedral intermediate, and then the oxygen will reform the carbonyl by eliminating the leaving group, giving us an aldehyde. And then as we know from previous reactions we covered, aldehydes are generally reduced by sodium borohydride to alcohols, so that is exactly what happens here. The aldehyde will react with the hydride, give you an alkoxide intermediate, which then is protonated by acid to give us a primary alcohol. Overall, we have done 2 additions of a hydride to this acid chloride, and we're able to do that because of the leaving group that we have on it. Now, sodium borohydride is a mild hydride reagent. It can only react with acid chlorides. It doesn't react with esters and amides. Lithium aluminum hydride, or LAH, is a very strong hydride reagent that can reduce not only acid chlorides, such as benzoyl chloride, into a primary alcohol, but it can also reduce an ester into a primary alcohol. And if we have a lactone, it will reduce it into a diol. In this last reaction, the hydride reagent provides a hydride to this ketone, ester, turning it into an alcohol and also eliminating the alcohol that is attached to the ester. As a result, we end up with 2 alcohols from 2 hydride additions. The reduction of esters is very similar to the reduction of acid chlorides with hydrides. It occurs twice. So The H minus from lithium aluminum hydride will be added to the carbonyl, breaking the double bond, giving you a tetrahedral intermediate, which then reforms the carbonyl by eliminating the leaving group, similar to what we saw with the acid chlorides. That gives us an aldehyde intermediate, which then gets reduced again. So a hydride will add to the carbonyl, carbon, break the double bond, and then that oxygen is protonated by acid to give us an alcohol, a primary alcohol. Amides are a little bit different when it comes to hydride reactions compared to esters and acid chlorides. For example, if we start off with this amide, when we add lithium aluminum hydride, instead of obtaining a typical primary alcohol, which we did with esters and acid chlorides, we get instead an amine. So let's take a look at the mechanism to see why that occurs. So the mechanism starts with a hydride adding to the carbonyl of the amide, breaking the double bond, giving us a tetrahedral intermediate. What differs here, though, in the mechanism compared to the ester and the acid chloride reduction is that the oxygen is actually a better leaving group than the nitrogen. And so as a result, the nitrogen will push it out as follows, giving us an iminium ion, which then gets reduced into an amine. Here's an example of what would happen with a lactam. With lithium aluminum hydride, we essentially remove the carbonyl completely to give us a cyclic amine. In this question, we want to predict the product that will be obtained from a hydride reduction of the following ester with lithium aluminum hydride. As you may recall, when we do a hydride reduction of an ester or an acid chloride, we typically obtain a primary alcohol. So the hydride, in this case lithium aluminum hydride, would add to the carbonyl once to give us initially an aldehyde by eliminating this phenoxy group, and then it would add a second time to give us the primary alcohol we see here, which is benzoyl alcohol. The phenol that you see on the right side is a byproduct from the elimination of the phenoxy group of the ester in the first addition of the hydride. In this question, we want to think about how we will prepare the following amine and ethyl aniline by reduction of an amide with lithium aluminum hydride. The reduction of amides to amines will occur as follows. So if we're trying to make this amine, we want to think backwards of which amide we would use. We would need to put the carbonyl to the right or the left of the nitrogen. And so since there's no possible way we could add a carbonyl here, the only possible place would be on the right side of the nitrogen. So this would have to be the amide we would need to use in order to make an ethyl aniline. Although thioesters and acyl phosphates are not very common in organic laboratories, they are extremely important in biochemical reactions. Acyl coenzyme A is one of the most common thioesters in nature. Here is an example of how acetyl coenzyme A can be synthesized. It starts off with coenzyme A reacting with this acetyl phosphate compound. The thiol group will do an acyl substitution on this acyl phosphate. It leads to forming acetyl coenzyme A, and notice we have an acetyl thiol ester as a product. On this slide, there's a couple examples of reactions that acetyl coenzyme A undergoes. For example, glucosamine, which has an amino group as well as several alcohols, reacts with acetyl coenzyme A through an acyl substitution to transfer an acetyl group to the amine in glucosamine. So the nitrogen attacks the carbonyl of the thioester to give you an amide in the product. Choline, which has an alcohol, can react with acetyl coenzyme A through another acyl substitution. Choline acetyltransferase helps in this reaction, which is an enzyme. The alcohol attacks, thus a substitution, and so now we have an acetyl group on the alcohol forming acetylcholine, which is an important neurotransmitter. Polymers are examples of very large molecules in chemistry that involve repeating monomer units. As an example, a diamine can react with a diacid chloride to make a polyamide. In this example, we're actually synthesizing nylon, which is one of the most important synthetic fibers. This type of reaction involves an acyl substitution. It is also a type of condensation reaction. We have covered several of them already. Condensation reactions are reactions where two molecules will join together to form a larger product, an addition product, leading to also usually a byproduct, a small molecule that is a byproduct. Here's another example of a condensation polymer, which involves a diol reacting with a diacid. And so one of the alcohols attacks the carboxylic acid through an acyl substitution to make a polyester. And if that reaction repeats multiple times, we can make a polyester or a polymer involving ester bonds. There are two main classes of synthetic polymers. The one we're looking at here is a type of step growth polymer where each bond is individually made, leading to a product and then reacts further. It can be the same type of reaction, but each step produces a new bond. Last semester, perhaps you encounter a different type of polymer, which was formed from the reaction of alkenes, adding a radical initiator, such as benzoyl peroxide, and adding either heat or ultraviolet light led to the beginning of the reaction. But once the reaction got going, multiple bonds would form consecutively in the reaction. And so that would be an example of what we call chain growth polymers, where multiple bonds are made in the same reaction. Let's take a look at other examples of condensation polymers. Nylon 66 is an important synthetic fiber. It can be made from a dicarboxylic acid, such as adipic acid, and diamine, such as hexamethylene diamine. If we heat the two, we can form an amide bond multiple times. So one of the nitrogens can replace the OH group on a carboxylic acid. And if we repeat that multiple times, we'll end up making a polymer, which we call nylon 66. Each reaction will make an amide bond, but that reaction continues, and over we continue to make amide bonds. Notice how we draw the product from one of these polymerization reactions. So we typically abbreviate the monomer unit that we're using. So in this example, we have the diamine, which we used, which was hexamethylene diamine. You can see that on the right side. And then on the left side, we have most of the adipic acid minus the OH group, since now the carbonyl is joined to the nitrogen. And then on this side, we have a carbonyl that's bonded to another nitrogen, which of course is not shown. It's shown on the right-hand side here as these units are repeating. We put this all in a parenthesis to put a subscript N to indicate that this monomer is repeating multiple times. Another example of a condensation polymer is dacron, which is another synthetic fiber that would be made from dimethyl terephthalate, which is shown here as a diester. It reacts with ethylene glycol, which is antifreeze, of course. This is a diol, and so you can replace the methoxy group to make an ester bond, and if you repeat that multiple times, you'll get the polymer. Again, the polymer product is abbreviated here in parentheses with the subscript N. Condensation polymerization reactions can also be used to make biodegradable polymers, and there are 3 examples shown on this slide. Biodegradable polymers typically will contain an ester bond, which is, of course, is susceptible to hydrolysis over time. There are 3 examples shown here. The first one is made by taking a compound that has a carboxylic acid and an alcohol, and of course, repeating these units multiple times. One alcohol from one unit can react with a carboxylic acid of another. Same thing happens in the other 2 examples. So we have lactic acid and we have this 3-hydroxybutyric acid. Each of them contain an alcohol and a carboxylic acid. Is an example of a thermoplastic. It's essentially a impact-resistant glass, which is made by taking a compound called diphenyl carbonate, which has a carbonate functional group. It's essentially an ester, except that it has 2 alkoxy groups rather than just one. This functional group reacts with alcohol similar to esters, and so if you heat them up, you can make ester bonds and therefore make Lexan. There are many important biological polymers, including cellulose, proteins, and nucleic acids. Cellulose is a polymer of glucose, so 2 glucose units can join together by the reaction of this alcohol and this alcohol on 2 different units. So that leads to the formation essentially of an acetal. So you can see here on this carbon, we have an alkoxy group in this direction, and then we have an alkoxy group in this direction. So that makes this carbon an acetal. So glucose itself is a hemiacetal, and if we take the alcohol unit of 1 glucose units and react here, it will lead to the formation of this bond here and essentially a formation of an acetal. Proteins are polymers of amino acids. So amino acids contain both a carboxylic acid and an amino group. And so one amino acid can react with its carboxylic acid with the amino group on a different amino acid, and that leads to the formation of amide bonds and therefore the formation of a protein. Nucleic acids like RNA and DNA are polymers of nucleic acid bases. So here's the structure of a nucleic acid base that would react involving the alcohol of one unit with the phosphate group of another to make these phosphate bonds and connect different nucleic acid bases. Let's take a look at this problem involving condensation polymerization reactions. So in this reaction, we have a dihalide and a diol, and we're going to add base to form a polymer from it. Now note this is not a acyl substitution reaction. Is actually a simple SN2 reaction, which we looked at earlier this semester. When we have a dihalide and a diol, and we include base, one of these alcohols will react with the carbon with the leaving group, doing an SN2 reaction. And if we repeat that multiple times, we'll eventually make a polymer. So that leads to a polymer that has this structure. And you have here on the left side the 3 carbons from the alkyl halide, and then that's bonded to an oxygen, which would be this one, let's say, with 3 more carbons, which would be the 3 carbons in the diol, plus another oxygen, and then a bond to the next unit. All of this is put in parentheses with a subscript N to indicate that we have a polymer of variable units. Let's review some of the reactions we covered in this chapter. So we're going to start with a carboxylic acid reacting with thionyl chloride. The next reaction involves a carboxylic acid and phosphorus tribromide. The third reaction involves a carboxylic acid and adding base and an alkyl halide, or we could do a similar reaction with ACl and an alcohol, which would be the Fischer esterification. And then lastly, we have DCC and an alcohol. All of these 3 variable or related reactions would give the same product. In the last reaction in the slide, we have a carboxylic acid, an amine, and DCC. In the first reaction, we're reacting a carboxylic acid with thionyl chloride, which typically converts hydroxyl groups, whether on an alcohol or a carboxylic acid, into a chlorine. So in this reaction, we'll get an acid chloride as a product. Phosphorus tribromide will convert a hydroxyl group into a bromine. If we start off with a carboxylic acid and we add any of these reagents, we can make an ester from it. So in the case of the first reaction here, we have a base that would deprotonate the carboxylic acid, which can then do a substitution reaction on the carbon with the leaving group to add the ethyl group on the oxygen. With ACl and an alcohol, ethanol, we'll be doing a Fischer esterification, which means the alcohol will replace the hydroxyl group to give us again this ester. And DCC can join ethanol and a carboxylic acid to make an ester. DCC can also be used to join an amine and a carboxylic acid and form an amide, as shown here in the product. If we add a carboxylic acid to a base, we're going to deprotonate that carboxylic acid, which will make it into a better nucleophile. And then in this reaction, we're adding an acid chloride as an electrophile. In the next reaction, we're adding lithium aluminum hydride to a carboxylic acid. In the next reaction, letter G, we're reacting lithium aluminum hydride with an acid chloride or an acid anhydride. And then lastly, adding acid or base and water to an ester or an amide. If we add sodium hydroxide to a carboxylic acid, it should deprotonate it, making it a better nucleophile, which should then attack the carbon with the halogen leaving group to make an anhydride. If we add lithium aluminum hydride to a carboxylic acid, we should get a primary alcohol. Lithium aluminum hydride will reduce an acid chloride or an anhydride into a primary alcohol as well. Sodium hydroxide or ACl plus water will lead to the hydrolysis of an ester or an amide. For most esters and amides, we usually also have to heat the reaction, although it's not shown in this particular example. Ethanol is added to an acid chloride or an acid anhydride to form the same product. And in this reaction, the next one, we have ACl and ethanol, or we can use sodium ethoxide to react with an ester. An acid anhydride or chloride can react with an amine to give the same product. And then lastly, we're going to react an amine, primary amine, with an ester. If we add ethanol to an acid chloride, we should get an ethoxy ester, as shown in this reaction. The same reaction would occur if we add ethanol to an anhydride. Adding Acyl in an alcohol to an ester should lead to a transesterification reaction, so the methoxy group will be replaced by an ethoxy group. The conjugate base of the alcohol that we want to add can also be added to an ester to do a transesterification reaction as well. A primary amine will add to an acid chloride or an acid anhydride to make an amide. So the nitrogen adds to the carbon with the leaving group, giving you an amide bond. Notice the product has the same methyl group as the reagent. Methylamine can also add to esters to give you amides, as shown by this last example. In this first reaction, we're going to add two equivalents of a methyl organolithium or a methyl Grignard to an acid chloride or an ester. In the next reaction, we're going to add a cuprate to an acid chloride. Next, we're going to add sodium borohydride to an acid chloride. In the next reaction, we're adding lithium aluminum hydride to an ester. And then lastly, lithium aluminum hydride will be added to an amide. Methyl lithium or a methyl Grignard will add to an acid chloride or an ester, and generally they add twice to give you a tertiary alcohol. So we're going to add two methyl groups in this example to the carbonyl to turn it into a tertiary alcohol. A Gilman reagent will transfer the methyl group or whatever other alkyl group we have and replace the halogen on an acid chloride to give you a ketone. Sodium borohydride will reduce an acid chloride into a primary alcohol. Esters and amides typically require a more reactive hydride reagent like lithium aluminum hydride. Lithium aluminum hydride should convert an ester into a primary alcohol. When it comes to amides, we typically get an amine since the oxygen is a better leaving group than the nitrogen. Once we reduce the carbonyl once, that alcohol that forms typically is eliminated by the nitrogen and eventually reduced again into an amine. Here we're going to attempt the synthesis example, starting off with an alkene which has 1, 2, 3, 4, and 5 carbons, and converted into an amide which has 1, 2, 3, 4, and 5 carbons, plus the two methyl groups on the nitrogen. In this synthesis, we want to make an amide, which we can make from a number of acid derivatives, including carboxylic acids. And as we know, carboxylic acids are products of the oxidation of primary alcohols. And then primary alcohols, we learned earlier this semester, they can come from alkenes. So hydroboration on an alkene typically gives you anti-Markovnikov addition of an alcohol. And then that primary alcohol can be oxidized with chromic acid to give you a carboxylic acid. And then doing one of the reactions we learned in this chapter, we can convert a carboxylic acid into an amide by adding an amine and DCC.